So, welcome back. So, we will continue discussion on Schroedinger equation, which we started in the previous class. Now, we consider Schroedinger equation with a potential. Okay. So, before that I would like to make some comments, some references and other things regarding the heat equation, or more generally the parabolic equation. You can refer to Friedman's book. So, Friedman has, this is A. Friedman. This title is Partial Differential Equations. Okay. So, in fact, you see in the second part of this book a lot of discussion on semi groups, even autonomous semi groups. So, autonomous means, so you can even abstract Cauchy problem, we can put, see, so far we have considered only a operator, but here it also can depend on u. Okay. So, this essentially developed by Kato. Okay. So, you see lots of discussion on that. Also Keshavan's book, Functional Analysis and Applications. So, that is Keshavan's book. This also contains a discussion on hyperbolic equation, in particular wave equation. Wave equation we discussed in two Hilbert spaces. So, let me just, so one Hilbert space is this HD cross L2, and the main reference for this is Lax and Phillips scattering theory. And you also see some discussion on this in V. Petkoff's book. So, the title is Scattering Theory for Hyperbolic Operators. Okay. And for the Hilbert space H1 cross L2 also did that. So, this is essentially Paji's book or Keshavan's book. Okay. And for Schrodinger equation, so let me again just say that Schrodinger equation. So, main reference is Kato's book. So, this I earlier cited, perturbation of linear operators, that is one thing. And you also see a discussion on Schrodinger equation in Schester's book. This also I cited earlier. In fact, here you see multi-particle dynamics. So, Schrodinger equation what we are discussing is for a single particle, this is multi-particle system. So, you see a discussion in Schester's book, perhaps in Kato's book also, multi-particle system. So, one can write down a Schrodinger equation even for multi-particle system. And I, regarding this one, just want to make a comment, this regarding HD. Okay, this I feel there is still more to understand the relation between this HD and H1, okay, than just definition, but there is something more there. So, we need to analyze more about these two Hilbert spaces. Okay. So, with those remarks, so let me continue with Schrodinger equation with a potential. With a potential. Okay. So, this, so let me use a different symbol for the potential. So, just this is Laplacian u plus q u. Okay. So, I work only with R3. So, similar analysis can. So, this is the physical space anyhow. So, in other Rn, it is only of mathematical interest. Okay. So, last time what we showed was this Laplacian with domain H2. So, this is free particle, there is no potential. Domain H2 is a self-adjoint operator, self-adjoint operator in L2, operator in L2. Okay, and that implies by Stone's theorem, this I times Laplacian generates a unitary group. Okay, and that is so free particle. So, there is no problem there. Okay, so, with now, so we assume that Q is real valued. So, a typical example is the Coulomb potential, typical example is Coulomb okay, potential. Qx equal to, there is a constant. So, but I just mod x. So, in R3 that is locally integrable. Okay. So, that's typical example. So, this multiplier operator, so that's multiplier operator MQ. So, what does that do? So, it takes U multiplies by Q. Okay. So, this domain of MQ is set of all U in L2 such that again this QU is in L2. Okay. And so, that multiplier operator defines a linear operator, and this we have discussed in general. So, that is a densely defined closed operator, assuming that Q is finite almost everywhere. Okay. So, that is no problem. Okay. And now, we have to consider this operator. Okay. Consider the operator Laplacian plus MQ. Okay. So, with appropriate conditions on Q, we would like to consider this operator again HQ. So, that requires certain conditions on Q. Okay. So, it's just if you look at the multiplier thing. So, if you take U in H2, QU2 may not be in L2. Okay. So, that requires some conditions on you. Okay, and we want to apply after studying that. So, essentially we want to apply perturbation result again due to Kato perturbation result. Okay, so let me just recall, this is just in a general Hilbert space. Okay, so let H be a Hilbert space and A be a self adjoint operator in H. So, if B is a linear operator, B is a, okay, let me write symmetric linear operator in H such that dA is contained in dB, so that the operator A plus B is defined on domain dA such that dA is and B is A bounded with A bound less than 1. Less than 1. So, what does that mean? So, this Bx, so this is norm in H. So, okay, let me call it okay, plus B norm Ax, A and B are positive and B is less than 1. So, this is true for all x in T. Okay. So, you want to apply this Kato's theorem to the operator Laplacian plus MQ. So, already we have seen that Laplacian is a self adjoint operator with domain H2. So, you want to put conditions on Q, so that the domain of MQ contains H2. Okay, that is the first condition, and since Q is real, it is already automatically symmetric. The main thing is this estimate. Okay, so, this very crucial estimate, and that we have to obtain for the multiplier operator MQ. Okay, so, that is the program, that is the program, and okay. So, the main estimate is this one. So, let me call it as proposition. So, again remember n equal to 3. Okay. So, this arguments it is essential that n equal to 3. Okay. So, H2 is contained in fact. So, this is C and bounded. Okay. This is of course Sobolev lemma, because we are in n equal to 3, but we want a similar estimate. Okay. This, in order to derive this Kato estimate, we need this one further. So, u of x is less than or equal to C1 norm u. Okay, C1. Okay, let me. C1 epsilon to the minus 3 by 2. I will, how it comes, I will just C2 epsilon to the half so for all x in R3. So, this boundedness thing we want to quantify it. So, this is true for all epsilon positive and this norm is norm. So, this is the crucial estimate we need. Okay. So, proof. So, just okay. So, you again since you are working in the whole space this u cap. So, let okay. This is further for u in H2. Okay, so, that is for u in H2 we have this estimate. So, let u be in H2. Okay. So, using the Fourier transform definition, so we see that 1 plus mod chi square u cap is in L2. Okay. And that implies, okay, so this, so we write this u cap chi as, okay, let me write that 1 plus mod chi square minus 1 plus mod chi square to the u cap. This you have seen it many times, of course, just writing that. Okay. So, this is in L2 by the definition of H2 and this is in L2 because n equal to 3. Okay. So, here we are using that. So, this is in L1. Okay. So, if I take the inverse Fourier transform, automatically I get u is bounded. So, that is fine, but we want this estimate. Okay. So, now that is what we want to do now. Okay. So, taking inverse Fourier transform, we get, right. So, u of x is less than or equal to some constant, let me write that, integral u cap chi t chi, because we have concluded that u cap is in L1. Okay. Now, I write this one as C. So, 1 plus epsilon 4 mod chi to the 4 minus 1 minus half 1 plus. So, you pick any epsilon positive and just multiply and divide by this factor. Why these factors? So, again let me recall a similar thing. So, if I Cauchy-Schwarz, if A and B are positive, always write this is simplest thing, right. But suppose I want an epsilon factor to come here. Okay. So, what I do? I do this trick. So, this b by root epsilon, which is same as AB. Okay. And now, if I apply that Cauchy-Schwarz, so I get that epsilon. Okay. Of course, you get something here, but my main concern is to get an epsilon there. Okay. So, this is a similar manipulation. Okay. So, that so any epsilon you take, okay, and insert these factors. So, that is just 1, and now you use Cauchy Schwarz. So, this is less than or equal to. So, let me write that constant. So, 1 plus epsilon 4 mod j to the 4 minus 1. Okay, so, there is factor half, let me write that, and then similarly this one j for 4 u cap j square. And power half. Okay. And now this can be easily computed. Again n equal to 3 comes into play here, and this is just some constant into epsilon to the, because of minus 1. So, you get minus 3. Okay. So, this one, so let me write that. So, another constant, okay, just delta maybe. So, this is epsilon to the minus 3 half, and now look at here. Okay. So, 1 into u cap j square, and again by Parseval relation that you get u square, L2 norm of u square. Epsilon 4 is a constant, so we do not get anything there. So, just but again this mod j to the 4 u cap j square, that is precisely the L2 norm of the Laplacian square to the half. Okay. And finally, you just see that this is just C 1, same thing C, okay, epsilon to the minus 3 by 2 norm u plus this you get epsilon square here. So, that is why you get epsilon to the half. So, this is the crucial estimate. Okay. So, it also shows that, so this Sobolev, those Sobolev lemma says some continuity of some space into some space, but one can do little more analysis and obtain estimates in a required form. Okay. So, this is one of them. Okay. So, that is required here, and okay. Now you assume okay, this assume that q is real value, we assumed already, q equal to q1 plus q2, where q1 is bounded L infinity and q2 is in L. Okay. You check that the Coulomb potential 1 by x satisfy this condition. Okay. So, that is an exercise, satisfy this condition. So, that the potential can be written as sum of an L infinity function and an L2 function. So, that L2, okay, satisfy this condition. And you may also look into not just this one, you can also look into other such exercises. So, for which value of beta positive, okay, so you can write this potential as sum of an L infinity function and an L2 function. Okay. So, now we show that, okay, so that is this. So, when this MQ now becomes MQ1 plus MQ2. Okay. So, when Q1 is bounded, so just look at this, MQ1 u in L2. So, this is just nothing but q1 u square to the half, and that is just q1 L infinity norm of u. So, for all u in L2. So, in particular for u in H2. Okay. So, there is no problem for the bounded part. Okay. And for the other part, so this MQ2 again L2 norm. So, this let me write that. So, Q2 u square to the half, and here I want to use the L infinity norm for u and L2 norm for q. So, this is u L infinity into q2, this is L2 norm. And now, we have just shown that this is constant times epsilon to the minus 3 by 2 norm u plus epsilon to the half Laplacian u. This is as it is if u is in H2. Okay. And conclusion is that, so that implies H2 is contained in the domain of MQ, okay, and we have the above estimates. Okay. So, let us combine them, we have the above estimates. So, by combining, so here you see you get L2 norm here and there is an L2 norm here. So, we can combine that, and there is L2 norm of Laplacian. So, combining what we get is that combining the above estimates, we get what we get. So, this norm of MQU L2 norm is less than or equal to some constant. So, now this constant depends on even the L2 norm of Q1 and L infinity norm of okay, this norm of u. Okay, there is an epsilon also. So, let me put that, but here I want to put it specifically. Okay. So, first of all, so this proves, okay, this for all u in H2. Okay. So, this proves that MQ is Laplacian bounded, okay, and the Laplacian bound is C2, and this can be made less than 1 by choosing epsilon small. Okay. And so, that proves that again from the perturbation result, this proves Laplacian plus MQ is self-adjoint. Okay, so that implies further. So by Stone's theorem, so this I Laplacian MQ generates a unitary. Okay, and that gives the solution for the Schrodinger equation. Let me just write that and then continue in the. Okay. So this in turn gives a solution for the Schrodinger equation with a potential. Okay, of course, with some simple assumptions like that potential can be written as sum of an L2 function and an L infinity function. But of course, it's no way gives a way to write down the solution like we did for the Schrodinger equation without potential. Okay, let me just. This we do not have here, but what I understand even for the, and that is what Richard Feynman tried to write a famous formula, but you should check that even for the potential. So this solution what we call Feynman Car's formula. Okay, so I am not sure, but you should check that. Okay, I will stop here and we will continue in the next class, some discussion, further discussion.